is. I believe it's your job to assess where he lies on the continuum.
Good way to look at it.
It'll actually start affecting other sites of the spinal cord that's not associated with tissue damage.
But we're trying to understand, how the body works as a body, not just as a system of the body.
We are live with the Nets fan, Angelo, Collegiero, and Rossi G, the Knicks fan. We're going to talk about metabolism because it's just another day, and our metabolism is always going, What is metabolism?
Metabolism?
Metabolism? Yeah. I was talking to my mom yesterday. She's like, yeah, I'm older. You don't understand. My metabolism is slower. It's slowing down.
What does that mean?
Yeah, dude, I'm going to get into that. So yeah, that's what people generally talk about, right? Oh, my metabolism's slower than it used to be, or it's faster. I don't want to fast because my metabolism will slow down or whatever. Don't do that. So when people say their metabolism slows down, what they mean, a little bit more sciencey, is that their basal metabolic rate, so something called your BMR, is less. And this is generally due to anything that will cause metabolism. So muscle mass is metabolically active tissue. Certain foods, for instance, will increase your metabolism. They'll just increase the amount of calories or energy that you'll have to use, right? So your metabolism increases. And side note, usually people say, oh, my metabolism is slower. This is bad. In essence, your metabolism is slower. You're more efficient. So, that's what people talk about. They talk about speed of metabolism, but there's way more to it. And I never even think about that because that's silliness. It's pretty silly. So let's go through some other things. I think some other things that are important is what you're metabolizing, how you're metabolizing it, how you got that thing in your mouth, pause. And so let's talk about some stuff. So let's look at our food. Talk about that infamous carbohydrate. And everybody's like, oh, don't eat carbs if you want to lose weight. I haven't ate a carb. Just like in Step Brothers, I haven't had a carb in 4 years. You want to touch this shit? Want to touch this shit? There's some truth to that. We'll get into it, all right? So they don't want to eat carbs. They don't want to eat sugar. They throw out all these terms like refined carbohydrates. What does this all mean? It's a lot of just mumbo jumbo. Everybody's trying to get some money somehow. Everybody's trying to make the new diet to get money.
Trendy.
Everybody's trying to get trendy.
Bougie.
They're just fad diets, not fat diets, fad diets.
Fad.
Fad.
Like AD doctors.
Like AD doctors. Oh, I'm kidding you. Okay. So some people say, oh, you don't want to have sugar. You can have carbs, but don't have sugar. But carbs are sugar. They're the same thing, sort of. It's like a square and a rectangle. And the thing that people don't realize is they try and say this thing's bad, this thing's good. But when you're talking about physiology, there is no good, there is no bad. There is only contextual situations. So it's going to depend, the big D word, pause. So let's look at a refined carb. So just to get on everybody's level. So a refined carb is usually a type of carbohydrate that is not going to have that much fiber, usually. It's not going to have associated micronutrients like vitamins, nutrients, not as much. So we're talking about that white bread. We're talking about that pack of Skittles. We're talking about that Snickers bar. We're talking about that ice cream. It's going to have
anything that's in a box, pretty much, right?
Anything in a box. So they discuss that this is bad because it's not natural, or they'll have their own reasons. Then you have these things, unrefined carbohydrates. So these are more natural things, fruits, vegetables, anything you could find in nature that have carbohydrates in them will be unrefined. So they're going to have more fiber, they're going to have more associated micronutrients, and these are generally associated with being good. So a term that's thrown around with these words is glycemic load or glycemic index. And generally, things that are refined carbohydrates are going to have a higher glycemic index, which will be associated with a higher glycemic load. Things that are less refined or unrefined carbohydrates will have a lower, usually, glycemic index. And all that means is that they are going to, the lower glycemic index foods aren't going to spike your glucose as much. And why does this matter? We're going to get into all that. So if you have no idea what that means, doesn't matter. We're going to get all into that. So it's generally just going to spike your glucose higher. That's generally bad. So if you have a refined carbohydrate, there's not the fiber that's slowing down that digestive process. So it's going to get digested and put in the bloodstream really quick, high glucose, high insulin response, and that could be a problem. That's why people think it's bad. All right. So whatever you're eating, though, so that was just a quick intro. Whether it's carbs, fats, proteins, nutrients, anything, any food, you go through the similar processes. So before you even eat, it's around lunchtime. What happens? You start moving around, walking around the kitchen. If you notice, you are very movement. You're trying to move around. You're trying to do a lot of things when you're hungrier. And this might happen at a certain time. This might happen when you see something, when you smell something, you start salivating. Your digestive process actually begins before you actually start even eating anything. So that's the first thing that's going to happen. There's these neurological processes that happen before you eat something. Okay. So you put something in your mouth. You're going to have enzymes. So enzymes are just something that speed up a reaction. So for carbohydrates, for example, we're going to have these enzymes called amylase, more for starch. For proteins, we're going to have separate enzymes, trypsin, and fats as well, lipase. Okay? So you chew. You want to break it down, digest as much as you can in your mouth, and then that food gets pushed to your pharynx, and that food in your larynx, so it's a bolus, gets down to your esophagus. It's going to go down through gravity and through this mechanism, muscle contractions called peristalsis, and it's going to end up going through a sphincter, your lower esophageal sphincter, into your stomach. In your stomach, there's a lot of acids, gastric juices, things that are super acidic that are pretty much going to further digest this food. And at the end, it's going to, there's some different parts to the stomach, but it's going to turn your food into this substance called chyme. Chyme is going to get passed to your small intestine. Once you're in the small intestine, this is where things start to get actually absorbed.
I thought it was chyme.
Chyme? I think there's an H next to the C, and we're in America. This is
That might
America.
be a silent H.
Silent H? You have a silent E in your name.
Like Christmas.
Kala Oreo.
Mm.
Okay. So we have in the intestines, we have a lining around it. So this is where actually nutrients get brought to and absorbed. So this lining is like an endothelial lining, and they're called exocrine cells. And all these nutrients, whether you're a carb, protein, or fat, you're going to get brought there. There's different processes that need to happen first when you're in the small intestine for that transport to take place. Okay? And we have like a little, we're trying to stay on track here. Okay, so when you're in the small intestine, foods get brought to and from your liver. So your liver is a screening process. So it's not just for nutrients, it's going to deal with alcohol, as a lot of people know, and many other toxins, and it's going to screen things that come in your body, right? So if we look at fats, it could convert fats into triglycerides, for example. If we look at carbs, it could do a bunch of things with carbs. Proteins, it could do a bunch of things with proteins. It depends on your metabolism at the time, okay? And we have other things that happen. So from the small intestine, those nutrients can go to your pancreas, and your pancreas can do things. It could go to your gallbladder for bile. There's a lot of things happening here, okay? But that's just the general flow, okay? So if we take a look at, just for example, we have different types of carbohydrates. So they're all going to be digested a little differently. So when we take a food, say we take a complex carbohydrate, a polysaccharide, that is like, give me an example, like a bread, like a whole wheat bread. We'll have a lot of polysaccharides. Why are these good, quote unquote? Because they have to get broken down into disaccharides, and then those disaccharides get broken down into sugars: glucose, fructose, galactose, not fructose, glucose, galactose. And then these are going to get transported to that lining of the small intestine through different channels, and then it's going to get brought out eventually to the blood right outside of the small intestine. So the small intestine is really thin. I don't know how many cells thick. It might be only a couple of cells thick, the actual lining, and it passes right over to capillaries, so blood vessels, right on the other side of the wall, and that's where the nutrients get put out to. So they get put out to the capillaries, okay? So all of the different types of carbohydrates, all the fats and proteins go through this process, okay? And your small intestine is going to be the major absorption structure in your body. So your large intestine and your large intestine is going to absorb some, and different parts will absorb different things, but for the main part, small intestine is doing the job. So once we have these circulating in the bloodstream, we have glucose in the bloodstream, that's your carbohydrate. We have proteins or amino acids in the bloodstream. Then we have fatty acids, so triglycerides as they get stored, but we have fatty acids and glycerol in the bloodstream. We have all these things, right? So let's look at glucose. Let's look at the metabolism of that carbohydrate, that Skittle you ate. So one thing that can happen is this thing called glycogenesis. So you eat that glucose, it goes down, you eat that Skittle, it goes down, and your liver and your muscles, but let's just talk about the liver, is going to take up that carb and store it away as glycogen. And all glycogen is glucose, chained glucose. So it's a bunch of glucoses together. Okay? So we don't have to get too deep into that, but as, just for example, if your liver is really important for this reason, if your liver senses that your blood glucose is low, carbohydrates are low, what will happen? It has all this stored glycogen because of this process, and it's going to use that glycogen and create more glucose because your brain needs fuel, and your brain is going to use mainly glucose. It's the preferred fuel of the brain is glucose. So you're feeling tired, anything like that, it's probably because you don't have glucose and you didn't get to fats yet. We'll get there. So just as I just described, the next process is glycogenolysis or glycogenolysis, however you want to talk. I think Angelo calls it glycogenolysis.
I call it glycogenolysis.
Lama. So that glycogen is going to go from put together, something that was synthesized, and now it's going to get digested, broken apart, and get into the blood. So there's some key players here that we'll get into, but things like hormones, things like neurotransmitters are going to have, something just popped up on my screen, are going to have a large effect on this thing to happen. And we'll get into those, but bare basics. As far as energy production through carbohydrates, we have this magical process called glycolysis. So we'll only get into this a little bit. So this is one of the energy systems that you can use to create this energy currency called ATP. It is the dollar of the human body. So what ends up happening is you take this glucose. So we have this glucose, and it's 6 carbons. So carbon on the periodic table, 6 of them lined up. What does it do? glycolysis. It splits. Lysis means split. So it's going to split that glucose into 2 separate molecules. So 3 and 3. So 3 carbons and 3 carbons. These are each, they're actually each, they're P-gols. It's different, but they're separate molecules, and eventually they're going to become this 3-carbon molecule called pyruvate. Okay? And what ends up happening is you generate, through this creation of pyruvate, 2 ATP per side, per pyruvate. It takes 2 ATP energy to go through this process, and then you have 2 ATP net per pyruvate molecule you create. So this process gives you 2 ATP. Not a lot compared to the other, but it's really fast. And if you look at a cell, where does it happen in the cell? It could happen anywhere. It doesn't have to happen in a specific organelle. It actually happens in the cytosol. So it's just very quick how this all goes down. But if you look at other processes, they're going to have to happen in the mitochondria when we look at the Krebs cycle. So that's very bare basic. So that's glycolysis. Krebs cycle, as I just said, and the electron transport chain, also known as the oxidative phosphorylation, there's many ways that this can happen, but how glucose is involved in this is pyruvate can actually be converted into the molecule that begins the Krebs cycle. So this Krebs cycle is mainly for lower intensity where you require oxygen, or you have enough oxygen to fuel the process. Glycolysis is more related to higher intensity, and this is very robotic because there's a lot going on, but this is textbook what you would learn. There's a lot going on, but for now, glycolysis is high intensity. You're playing basketball, you're sprinting up and down the court, you feel the burn, right? That's glycolysis. Oxidative phosphorylation, or Krebs cycle, is not like that. It's that steady jog where you don't really feel the burn, and you don't have this buildup of this substance called lactate or lactic acid. Okay? So Krebs cycle uses, as far as carbohydrates concerned, will use a pyruvate to convert it into this thing called acetyl-CoA, which begins the Krebs cycle, eventually going through the electron transport chain, and it's going to produce around 32, not around, exactly 32 ATP. Okay? So you would think, wow, it's 16 times more ATP. Why don't I just use Krebs cycle? This happens in the mitochondria. As Angelo is probably, I'm not sure, probably going to get into the fact that mitochondria is not really this circular thing, but it's more of a reticulum. You might get into that. I really don't know.
I was, but you just stole my thunder.
No, we'll get into it. So you're getting all this extra ATP, but it's so slow. So it's an efficient process in the fact that it gives you way more, but it's an inefficient process is that it's slow. So it's not going to go to that process first, but they're going to kind of get used at the same time. We'll get into it. Now, this other process of carbohydrate metabolism is this thing called gluconeogenesis. All this means is you create glucose from non-carbohydrate molecules. So, for example, you could create glucose from fats. You could create glucose from amino acids. You could create glucose from pyruvate molecules. You could create glucose from lactate, etc., and their derivatives. So you can create glucose from protein and amino acids. You can create glucose from triglycerides stored in the liver and free fatty acids and glycerol. You can create glucose from the derivatives of glucose, which is pyruvate and lactate. So when you're doing that high intensity stuff, this is a really important process because in order to not feel the burn as quickly or get above that anaerobic threshold, anabolic threshold, the threshold at which you produce a lot of muscle at one time, anaerobic threshold, it will delay you hitting the anaerobic threshold because it's going to take a lot of that lactate, that byproduct, the bad stuff, and it's going to take it, but that lactate's actually your main fuel source, and we'll get into that. It's going to take it.
That's not what causes the burn, by the way, guys.
It's not. This is all textbook I'm giving you, okay? through this process called the Cori cycle. It's going to take that lactate produced through glycolysis, the splitting of glucose, and it's going to make new glucose and send it back through. So some elite athletes might be really efficient at this. Their lactate threshold, the threshold at which they have too much burn to continue, might be low. But this Cori cycle process might be super efficient in them, and we'll get into this, depending on different factors. There's a different way to train in order to make this process more efficient, right? So you want to train for specific adaptations and actually know what you're going for when you're training, and not just get in there and get taught to go around the gym and, oh, let's hit this machine, that's open. Let's hit that, this is open. Okay? What's the next thing on our list? So I really wanted to go through glucose metabolism because I feel as if that is the most important. And Angelo is going to use that as a springboard, essentially, as far as what I understand, and go into a lot of things around that. But just real quick, just to touch upon, fat metabolism is very similar. So there's a lot of different things happening. So you can get this thing called lipogenesis, if you can guess, creating triglycerides, stored like triglycerides. If you could do that, guess what else you could do? You could take those triglycerides and mobilize them as free fatty acids and glycerol in the bloodstream for energy once glucose isn't there. Glucose is your preferred energy source, quote unquote. Then fats, if they're available. No fat, then probably more protein. So you can create fatty acids through your liver. You can go through this process called beta oxidation, where you go through the Krebs cycle, and those free fatty acids are turned into that enzyme called acetyl-CoA. You could go through ketose production. So there's a lot of things that can happen. And one important function, Greg hit me up, of this is of lipids, so fat, is cholesterol synthesis. And cholesterols are important for a ton of things, like your cell membranes, to translocating things around your blood, stirred material. So without further ado, I give you the Oreo.
All right. So after all that, let's take it into a little bit more of a clinical scenario. Let's talk about diabetes for a little bit and insulin. So you mentioned insulin briefly. It's pretty much the transporter for glucose within the blood. Insulin actually has several different roles in the body. It's not just the transporter for glucose. But for this context, we'll just say it's the transporter for glucose or blood sugar. Once this insulin glucose complex, so glucose binds to the insulin, once this complex of insulin and glucose reaches its target tissue, it binds to an insulin receptor on the membrane of that cell. This sets off a cascade of chemical events within the cell, which ultimately brings this GLUT4 transporter, it's called, to the membrane. So now the GLUT4 transporter grabs the glucose from the insulin and brings it into the cell so that the cell can use it as fuel. In the end, that's the main goal. So to make this a little easier to understand, I've made up a little analogy here. Pretend you went out to buy some groceries. When you got back into the parking lot, you noticed your car was stolen, so now you don't have to ride home. So you call a taxi cab. So that taxi cab is the insulin to pick you up with the groceries. So you and the groceries are that you can be the glucose. The taxi cab, the insulin, brings you the glucose home and parks in the driveway. Now your lovely children, they just love to help you out. They see you outside with a bunch of groceries, and so they run outside and take the groceries inside for you. So your children are the GLUT4 transporters. Now the groceries are inside your house, and you can make dinner, meaning you can fuel your family, right?
Wow, that's really good. Holy shit.
It's a little analogy I made up. So type 2 diabetics So the kind that you get from usually living an unhealthy lifestyle rather than the more hereditary type of type 1 diabetes are usually referred to as insulin resistant. Remember that term, insulin resistance. According to this, the insulin receptors, or the welcomers, on the cell membrane are unable to bind insulin. So for some reason, that taxi cab isn't able to get into that parking spot. And again, this is textbook. This is what you're taught. Therefore, go ahead.
You might want to move your mic away from your
Sorry.
epiglottis. Yeah.
Is that better?
Yeah.
Okay.
No, I think you were good.
So, so according to this insulin resistance term, and again, that's textbook, and I think everyone now knows by now, whenever we say that's textbook, that means we have a little bit different of approach to it or idea of it. But according to this, the insulin receptors, or the welcomers on the cell membrane, are unable to bind insulin. So that parking spot in your driveway is unavailable for some reason. Therefore, the glucose can't be taken into the cell. And in turn, the glucose stays inside the blood, which is seen as high blood sugar. And you're told you have diabetes once this level of blood sugar gets to over 126 milligrams per deciliter of blood. In reality, it's actually just a spectrum, but in the healthcare system, once you hit 126, you're a diabetic. So these patients are given medications that pretty much help to force glucose into the tissue cells so that it isn't floating in your blood as much. And voila, your blood glucose is lower, so that must mean your diabetes is improving, right? However, go ahead.
It's voila. It's a French word. It means here it is. Voila.
Oh, voila?
Voila. Yeah.
Oh, okay. Well, so now, voila, your blood glucose is lower. And so that means you must be improving, right? Your diabetes must be improving. However, as we all know, these patients end up progressively getting worse and worse and end up getting prescribed large doses of insulin on top of those medications that didn't previously work in more an attempt to force glucose into these cells. They ultimately continue to progress, with the common symptom being diabetic ulcers and infections, which lead to amputations and ultimately death, as people who get these amputations generally don't live beyond 5 years post-surgery, post-amputation. Generally, the symptoms of diabetes progresses and these patients die of multiple diabetic-related complications.
Can I interject?
Yeah.
If you're someone listening and you're saying to yourself, I don't have diabetes, why do I need to know this? Angelo, would you think it's fair to say that just because on one side, just because you're over that 126 grams per deciliter, is that the unit?
Yep.
Milligrams per deciliter of glucose, that doesn't mean your fate's sealed. You can do some things to lower it. On the flip side, if you're at 124 milligrams per deciliter, that doesn't mean you're all is well. Like you said, right? Everybody's on the spectrum. So where do you lie on the spectrum is an important question. And everyone can improve as far as these metrics. Probably not that metric, as we'll get into. But this is important for everyone. This is important for me. This is important for Angelo. This is important for anybody listening, not just someone that gets the diagnosis of diabetes, to put in a box person.
Right. And yes, like you said, it's a spectrum. So, and I think also understanding the physiology of what actually happens and the science of what actually happens will help you, no matter what you, if you're a clinician or if you're one of us who has patients. It will help you if you're just trying to better yourself or get healthier. So I think just understanding this concept is important, and explaining it in terms of diabetes to me is just something where a lot of people can relate and a lot of people know a decent amount on. So yeah, as I was saying, that these people usually get worse and worse, and they ultimately end up dying of some sort of diabetic related complications. And there are multiple of these complications from a variety of ranges. So since this treatment approach and the term insulin resistance doesn't make sense to us. We've kind of been researching a lot and listening to a lot of podcasts, and I'll give credit to Dr. Peter Attia and Jason Fung, because we have been looking at a lot of their work, specifically Jason Fung on this topic. And something that he sees in these diabetic patients is that the liver is actually undergoing extremely high rates of what's called de novo lipogenesis. So as Ross was saying, the liver does a lot of things. One of them is de novo lipogenesis. I just said, I'm sorry. That is the liver of these patients is converting glucose into triglycerides, or just storage form of fats, at an unusual high rate compared to healthy individuals. So their de novo lipogenesis is extremely high in these diabetic patients. So how is it that insulin receptors on the wall of the liver are insulin resistant, meaning that glucose can't get in, right? That's what that means. But yet the liver is somehow converting so much glucose into fats so that it can be stored somewhere else.
I have a question.
Go ahead.
That process requires insulin, to my understanding. That's one of insulin's alter roles is storing triglycerides.
Yeah, it helps. Yeah, and in this context, it helps. It brings glucose to the liver, just like it brings glucose to any other target tissue. It brings glucose to the liver so the liver can do as it may, whatever it needs to do with glucose, whether that's turning into glycogen to store glucose or turn it into fat to store as fat. If you're someone who doesn't use a lot of energy and doesn't use a lot of glucose in their metabolism, as we'll get to later. So in other words, how do these patients exhibit extremely high rates of de novo lipogenesis without, if they're insulin resistant? Because if they're insulin resistant, that means that the insulin won't be able to help get glucose into those target tissues. Another way of looking at it is how can you build a log cabin without any logs? If there's no way that those logs are getting there, how can you build a log cabin? So it really doesn't make sense physiologically, but yet these patients are still told that they're insulin resistant and they need to just lower their blood glucose, because people think diabetes means blood glucose levels, high blood glucose levels. And there's truth to that, but that's not the whole picture. That's not the only thing that's going on. And we're not saying that that's completely wrong. We're just saying there's a lot more to it that might help you make sense of all of it.
So I think the way I see it is that blood glucose is the metric that a lot of people are using as far as their health.
Yes.
When in fact, it's not just about their blood glucose, because as you're saying, the glucose in your blood can be high or low, and you could still have a lot of associated problems elsewhere.
Yeah, and I think it's a good start, especially in this context. I think blood glucose levels can give you a lot of information about what's going on, especially according to this podcast episode, metabolism, especially in the metabolism context. It can give you a lot of information about what's going on. But the problem is people think diabetes is just blood glucose, when in reality, it's total body glucose. So as I'll get into in a little bit, a lot of these medications that are given to people are just help to force that glucose into other tissues, and then it's gone, or not gone, it's in other tissues, but you can't measure it in the blood now, so you have lower blood glucose, and so you're seemingly getting better, right?
So it's like storing a garbage, stuffing your garbage can filled,
yeah,
and you're hiding all the garbage.
Yeah, you're putting all your garbage in your closet. So, okay, yeah, this house is very clean. Yeah, and then you open the closet and it stinks like shit, and there's shit growing in there. So now that we're aware of this kind of misconception about insulin resistance and diabetes, although it's not completely wrong, there's just a lot more to it. Let's look at a little bit of what's actually going on at a deeper level, maybe, and add some more factors into it. So poor lifestyle choices are definitely what probably got them there in the first place. As Ross said, you eat some bad foods, most of them being boxed foods or just pretty much.
But just to conversate, this is not a blame thing either, because this can be really tough, especially when you go through periods of utilizing glucose as fuel partitioning. So you are primarily using glucose and you've been really efficient at using glucose, and all of a sudden you've had a huge lifestyle change where you're not using glucose as much, and then you could run into problems. It's not, so you could be the healthiest person in the world, quote unquote, as far as your diet goes, but if your lifestyle changes and you're not eating accordingly, then we could run into some issues. And I want to bring up an example later on, I think, about this.
Yeah, that's true. That's 100% true. So let's look at a real problem besides the poor lifestyle choices or the unhealthy lifestyle choices, I guess you could say, or maybe, as you just alluded to, the drastic shift in your diet, perhaps, that will cause some of these issues as well. But this term called hyperinsulinemia, and as opposed to insulin resistance. So hyperinsulinemia happens when there's so much sugar or glucose inside these patients as a whole that insulin is actually overproduced by the pancreas in order to get this glucose into the liver or to its target tissues. Liver is just a major area where a lot of the glucose goes, especially if you're not doing a lot of exercise. It brings it there so that the liver can package it and do as it needs. So you have a whole lot of glucose, so now you need to make a whole lot of insulin from the pancreas. The beta cells specifically in the pancreas produce insulin. And now that it's in the liver, it can be converted to triglycerides so that the body can now store it as fat. And this sets off a cascade of events that leads to even higher levels of blood glucose, abdominal obesity, and other symptoms that are actually just trying to protect yourself from the unhealthy shit that's going on in your body at the extremely high levels of blood glucose. So this makes sense as to why diabetic patients are seen with high levels of de novo lipogenesis in the liver,
Yeah.
because
Yeah. It's in your epiglottis.
so the liver becomes what is known as fatty liver as it accumulates with these triglycerides. Eventually, the liver has no more room and decides to transport these triglycerides to other visceral organs, such as the pancreas, which produces the insulin in the beta cells of the pancreas. So now the pancreas can't make and secrete insulin since it's clogged with all this fat. And in turn, your blood sugar continues to rise and insulin can't be produced anymore because now you have an issue with your pancreas. Now your blood sugar is going up even more and more and more, and you just get prescribed more shots of insulin to fight the high blood sugar. So in type 2 diabetes, usually you're not given insulin in the first place. You're usually given, like I said, medications that will try to force glucose into tissues and via other mechanisms. But now you're given insulin because they say, oh, for some reason you don't have a lot of insulin now, so let's give you some insulin. When in reality, the reason why they don't have much insulin is because of hyperinsulinemia. So it's kind of a paradox. But if you followed me, it would make sense. So this visceral accumulation of fat is called abdominal obesity, which is a symptom of diabetic patients and a part of the metabolic syndrome. So the metabolic syndrome consists of these 5 quote unquote risk factors. So a lot of times people say that if you have these 5 things, you're more prone to stuff like diabetes or other complicated heart diseases or other complications. The 5 factors that I'm talking about are high blood pressure, high blood sugar, excess fat around the waist, which is the same thing as abdominal obesity, high triglyceride levels, and low levels of HDL. So HDL is the good type of cholesterol. As Ross was saying, cholesterol is very important for a lot of processes within the body. However, there's some cholesterol that are protective and some cholesterol that are not so good and lead to other things.
So essentially, the thing that is diagnosed as diabetes and called diabetes clinically. So a part of this metabolic syndrome that you're talking about, so these 5 different things, one of them being high glucose. So typically that means diabetes, because diabetes is measured by a certain level of fasting glucose. And if it's above this amount that we talked about, the 126
Milligrams per deciliter.
milligrams per deciliter. So is that like a misconception about diabetes and its isolation? It's not isolated. It's kind of correlative with these other metabolic processes.
Yeah, I think it's a symptom rather than the cause. I think the cause can be, and besides the fact that you alluded to earlier of, there can be other seemingly not unhealthy but other ways to get your blood sugar high that might lead to unhealthy events physiologically, but I think the cause would be the unhealthy lifestyle choices, right? And then as a result, as a symptom, you get all of these factors within the metabolic.
You want to relate this back. So for our non-science listeners, so people that don't have a background, let's relate this back. So when we say unhealthy choices, what do we mean?
I mean, most of the carbs you consume are boxed foods or processed foods. As you alluded to earlier, they're not the natural or whole food type foods.
So I'll connect this back for people listening. So what I said before, and so it doesn't seem as random, I kind of wanted to push that. So it doesn't seem random, the jump that we made from what I was talking about to what Angelo was talking about is those bad carbohydrates, those refined carbohydrates. If we remember, they don't have that associative fiber. They get taken out. So what happens? Like I said before, they get digested, they get absorbed quicker. They have a higher glycemic load. It's like Dora the Explorer. Over the bridge. Yeah. Glycemic load, glycemic index, glycemic load, depending on how much of it you're eating. So things that have a higher glycemic load that you're eating, they're going to increase your blood sugar quicker. That's going to have a proportional insulin response or over proportional insulin response.
Especially if you continue to eat these things in the absence of exercise. Therefore, in the absence of energy utilization. So this might not be a bad thing for someone who's running or for doing sports. Like Gatorade, they're filled with these simple sugars, these high glycemic load type drinks such as Gatorade. They're not a bad thing necessarily all the time. They could be good because since they are quick and they absorb in your body very quick, they're good for athletes sometimes, to an extent. Nothing is good in heavy doses, but if you needed a quick burst of energy, then instead of eating something like a vegetable or a fruit where it takes a while for that carbohydrate to be broken down and absorbed into your body, you can drink one of these high glycemic load drinks and boom, you have energy much quicker.
That's not to say that there isn't natural, quote unquote, or organic, quote unquote, foods that have a higher glycemic load. So you can definitely take that route. But as Angelo's saying, people want to label this is bad, this is good. No, there is only context. So if we need that sugar quickly, we know where to go. And it's important to schedule that around your exercise, because you're a little bit more sensitive to nutrients after exercise, generally, and you will utilize those nutrients before exercise. And all this is doing is blunting, in a way, your insulin response, so that you don't have this magical thing called hyperinsulinemia, or you don't have this thing called what? Called high glucose, called hyperinsulinemia, and then all these associated problems.
Yeah, and so it pretty much happens. You have high blood glucose, and you can call it even resting high blood glucose, because if you're just going throughout your day and you have extremely high levels of blood glucose, then that's pretty unhealthy. But if you just ate a bag of Skittles and your blood sugar shoots up, you're probably diabetic for a few minutes, but then all of a sudden you're not diabetic.
Literally.
But yeah, so if you have these high levels all the time of blood sugar, then how does your body respond? Well, it produces a lot of insulin, and then over time, the large amount of blood sugar gets converted into fat so that your body can store it. And where does that fat go? It goes to stuff such as your liver stores it within itself, because that's where it's made. But then all of a sudden it's like, okay, we're full here, we got to push it out somewhere else, and it starts throwing it to its neighbors, and the pancreas is a neighbor, and the pancreas also makes insulin, so the pancreas gets clogged with fat, and now it can't make insulin, and that's where you get the even more progressed symptoms of diabetes through that hyperinsulinemia, even though now you don't have that much insulin.
And even before it gets processed and metabolized as fat, it's going to just stay as glycogen until you're full. And that's what Angelo was trying to say, is this word is thrown around and it's taken for granted that it's true, this insulin resistance, when it's not about the insulin molecule itself as the problem, the hormone itself. It's about the fact that you're just full. You just can't take anymore. So your muscles and your liver are the main hubs of this glycogen, this stored glucose. So as I understand it, if you're just storing, it's not the insulin, it's the fact that you're just having too many carbs in correlation with your lifestyle.
Right.
LeBron James will have way more carbs during his season than you will. So it's not about, oh, this is too many, this is too little. It's all about context.
He's also burning them at extremely high rates.
Exactly.
So it depends. It's the context, right? So going back to the metabolic syndrome a little bit, you got high blood pressure, high blood sugar, excess fat around the waist, or as we said earlier, abdominal obesity, high triglyceride levels, and low levels of HDL, so low levels of that good cholesterol. So now let's look at how all these factors can actually just be seen through a lens of symptoms of hyperinsulinemia and unhealthy lifestyle choices or diabetes. High blood pressure, let's look at that. Well, as we said, when you eat shitty foods that come in a box, you will then have increased levels of resting blood glucose, and because of this, your blood can actually get a little more viscous, which causes your heart to have to pump harder in order to push this blood through your vessels. This is very simplified, and there's many other things that are going on, but pretty much your blood now has to push a fluid with a texture more like an engine
Ketchup.
oil, or ketchup, rather than like a water or blood. We all know normal blood. So it has to push a lot harder, and that puts a lot of strain on your heart, and then that's how that could lead to cardiovascular issues. High blood sugar, well, pretty similar, but as we just talked about, as we've seen, when you make unhealthy lifestyle choices, such as your poor diet or the lack of activity to burn this sugar to prevent it from being stored as a fat, then now you'll have high blood sugar. So as mentioned, we got into this a lot, and it will progress into things like hyperinsulinemia and set off that whole cascade of events. Now, excess fat around the...
Just to say, not to discount, and just as you said, I really like that. So we're not discounting this whole problem of high blood glucose. That's not the idea.
No.
We're just saying it's one of the things happening. And probably the first stone to hit the other dominoes is the hyperinsulinemia. That's what we're saying. So yeah, there's problems when your glucose, as he was talking about with high blood pressure, will build up in your vessels, but then also it can destroy your vessels through different problems. And this is why people with diabetes have to get amputations for multiple reasons. They get infections, they get necrotic. So their tissues around certain areas that are more on the periphery, like their legs, will become dead because they're not getting blood, because their blood vessels are destroyed and they have to cut them off. They have to amputate them because then they're going to get infected.
Well, yeah, not only that, it's now you have so much of this glucose living around and you don't have a lot of insulin. There's nowhere for it to go because you're full in all the cells. So now glucose just gets pushed everywhere. And so a lot of people have, foot amputations or toe amputations who are diabetics and infections because these little microorganisms that cause infection, well, they can feed off of sugar too. So when you have all this stored glucose and this clump, this glob of food, pretty much it's pretty much.
And guess what else feeds off glucose?
Humans.
Cancer.
Oh, cancer.
What'd you say?
Humans.
Yeah, cancer.
And we can.
And
Yeah.
insulin too. Insulin plays a role in cancer. So insulin is going to help that process of mTOR that's not just in the muscles. And for our level 1 listeners out there that don't have a big science background, mTOR is just a signaling pathway that promotes anabolism. So your ability to have growth. So for cancer, this is a process that is really looked at. So glucose is going to play a factor. Insulin is going to drive the mTOR pathway. Then we have things that are going to help deter that, and that's what we're going to get into later on. But what were you going to say?
Yeah, and before I get back to the metabolic syndrome, now that we're on this cancer thing, and there's a reason why prevalent studies have shown that diabetic patients have such a higher risk of heart disease and cancer because of simplified, but what we had just said, and it's related to the jam-packed cells of glucose and that whole cascade of events that we already went through.
And what are cancer and cardiovascular disease? The number 1 and 2 leading cause of death.
Right, and they're
in America at least. And why do they both generally happen?
Because they are both diseases of extreme cell proliferation. In other words, overgrowth of cells.
Hyperinsulinemia. So this is important, people.
Yeah, and for this context, that's where we'll stop with that. There's a lot on that, though. So going back and relating it a little bit to metabolism and utilizing fuels for energy, let's look at mitochondrial efficiency. So let's compare the efficiency of burning fuel for energy of elite athletes to diabetic patients. So to do that, let's look at the mitochondria in both of these populations. The mitochondria, as Ross said earlier, stole my thunder, but it's the part of the cell which is actually a network of tubes, so like a reticulum, rather than in that little bean-shaped part of the cell. That's how we're taught. It's a little bean-shaped, but that's really not the case so much. But whatever, if that's how you make sense to you, that's fine. So in the mitochondria, this is where fuel sources such as fats and lactate, which is that byproduct of glycolysis, such as fats and lactate, can be converted into energy for the cell. So in elite athletes, specifically endurance-based athletes such as cyclists and runners and swimmers, so people who have a very high lactate threshold, as Ross alluded to earlier, their mitochondrial density, so the amount of mitochondria per
capita
per area of the cell increases. So that's just an adaptation to their training. They need more use of their mitochondria. So how does their body react? It's pretty smart. Your body's pretty smart, and they just form more mitochondria. And they're also super efficient at burning these metabolite, or not metabolites, burning lactates and fats for fuel. So they tend to not have a buildup of metabolites, and they can ultimately last longer in activities because they can quickly use these fuel sources, and they don't build up, and other byproducts don't cause them to feel the burn, and they can keep going. That's very simplified, but that's for another podcast, I guess. Energy systems. On the other hand, diabetic patients, their mitochondria are extremely inefficient, and this is shown in several studies. This isn't just something I'm pulling out of my ass to make sense. Therefore, the lactate and the fats and the carbohydrates that are burned less, and they tend to accumulate in these patients because their mitochondria are just not as efficient. They got stupid mitochondria. They don't know how to use these fuel sources, and this leads to a decrease in exercise tolerance and an accumulation of blood sugar, or that glucose, because you can't use it as fat as good, or you're just not exercising, so you're not using it, and fats, and they get stored throughout the body. And again, it sets off that whole cascade of events. But let's take this into a more clinical approach. So let's say we have some patients here. So let's relate this to a basketball player. You're a basketball player. So let's give
NBA, baby. NBA
Yeah.
sweatshirt for our audio listeners. That's what I'm wearing.
Yeah, he's in the NBA. He just got drafted by the Portland Trail Blazers, actually. Congratulations, by the way.
I took that 3 spot that they don't have. Stop it, Ross. No ums. So, basketball player. Yeah, so like I was saying before, I wanted to relate this whole thing back full circle. And now that I'm thinking about it, let's look at a lot of athletes. What happens to elite athletes that play a high intensity sport, football, basketball, things like that, tennis, high intensity, they're running glycolysis fast. They're using glucose as fuel. What happens when they stop playing, and a lot of them stop exercising because their only form of exercise would be for the purpose of their peak performance? What happens? They start to get more fat. They probably, to peak their performance, they probably didn't have this thing called metabolic flexibility, which is probably the most important thing as far as preventing this hyperinsulinemia, or as we'll get into, curing this hyperinsulinemia. They aren't able to switch between using carbs as fuel and fat as fuel. And these are two processes that we're supposed to use. So they're using glucose as fuel, and they're always told by their trainers, by their doctor, eat a lot of carbs, have pasta parties, this, that. It's a cultural thing. So there's a lot of different factors. And they feel great, they perform well, and it's all well. And during the season, they should be doing that because carbs will be more efficient at producing the thing that they want. Because they're at really high intensities. And like I said before, glucose is way faster. Glycolysis happens way faster and glucose is used way faster than fats, because what it happens doesn't have to go to the mitochondria. It happens within the cytosol of the cell, anywhere in the cell. So it's way quicker. And when people stop exercising, they still are eating the same. They don't change their eating habits, or eating habits drastically enough that they're matching their energy demands. So if they're not doing any more high intensity things, I would say at least significantly decrease your carbohydrate intake in some way if you're not going to be exercising in that way. Because what's going to happen? You're going to eat a lot of carbs still, and eventually over time, your blood sugar, as it keeps spiking and it doesn't get offset by the exercise, your insulin keeps going up. Your glucose keeps getting stored in your muscles. And then once it runs out, and it runs out in your liver, you start making fat, and that you get fatty liver disease, fatty pancreas disease. And that fat then eventually, it can't fit in there. It gets through the lipoproteins, like I was talking about, it mobilizes to other areas, and you get a large waistline and all these other problems. And then the glucose stays high in the blood, this hyperinsulinemia cascade. So that's how that happens. But as it relates to, say, a basketball player that is playing, like I just said, carbs are the fuel source during performance, no questions. Carbs. So I didn't say glucose because it's a little touchy, and I'm not too clear about it, and I don't think I'm astute enough to talk about lactate's role in all this, because it seems to be that lactate is probably the primary fuel source in a lot of what's going on. But carbohydrates, we know carbohydrates will fuel your performance better than fat. We know that. That's pretty.
Especially for, like you said, like in other athletes, like football players, like the average play is 7 seconds, so they are trained to peak for a 7-second duration of time. So they're not. That's too quick. That's too small of an interval to even touch fats as fuels. If you look at the efficiency and how it's burned, as Ross was talking about in the beginning of the podcast. So all they've done for their whole life, pretty much, because most of these elite athletes start playing these sports when they're young, all they've done is learn how to use carbohydrates as fuel. They've never really had to run a marathon. They've never really had to use fats as fuel, whatever exercise that may be, but they never really had to mobilize fats as fuel because of, one, their diet, and two, their training adaptations, and three, just the nature of their sport. That's just what they don't have. They don't need fat as fuel. So just like if you don't use your mitochondria and your mitochondria gets stupid and doesn't know how to work, it that's exactly what's going on, that you don't know how to use fats now. So as Ross was saying, when you stop playing these sports, when these people retire, they get a little older, their activity declines, but their diets tend to stay the same, and they're not burning it though. So that's where it becomes an issue.
Yeah, and it's not a burning calories problem, it's a fuel partitioning problem.
Right.
We'll get into that a little bit more. So, but if I need to convince you, and you're an athlete listening to this, and you're telling me, I don't give a fuck, I want those carbs because I have to perform this level for this reason. I want to convince you that there's a point in time where you should be learning how to use fat as fuel. And I'll tell you why. Let's go back through the process of glycolysis, how you're producing this energy, a lot of the energy. So like Angelo said, these football players, they're going to be spending more of their time in this other energy system called ATP PCR, where you're using stored ATP as fuel and you're using phosphocreatine as fuel. We don't have to get into it, but they're also using glycolysis a little bit. We're looking at basketball players. Glycolysis is probably the primary driver. We take that glucose, split it up, it becomes pyruvate. Some of that pyruvate turns into this thing called lactic acid. Your ability to run and keep going, so being really efficient, taking that lactate, putting it through the aerobic pathway, so the mitochondria, and somebody's at the door.
Continuing to use that for fuel.
So taking that lactate, putting it through the mitochondria, the inner membrane, and using it as fuel, or sending it to the liver and turning it back into reusable glucose, or just using that lactate itself, just as I said, and using that lactate as fuel for the Krebs cycle, using that pyruvate as fuel in the Krebs cycle, turning it into that thing called acetyl-CoA, that high energy molecule that enters the Krebs cycle. That is your ability to have repeatability, your ability to keep going, either not get to the threshold at which you say you can't go anymore because you're going too hard, too long. That getting there is going to take longer. So you're going to be able to stay in a high intensity state for longer. On top of that, you can improve your performance over time. Your ability to recover is going to be way more efficient. So you're going to feel better day to day if you have that called an aerobic base. So I think it's unquestionable that this definitely fits in an off-season program for anybody, even if you're a shot putter. if you're a shot putter, I can make an argument that you should have some level of aerobic base as far as long-term development. I could definitely make a case. So I think it's unquestionable. And if you have any more about that and you want to ask about, should I be doing this, should I be doing that, let me know. And I honestly think most people, and it gets a little bit better as you get older, as you go into college and then professionally, you get a little bit more exposure, more likely to get more exposure to more thoughtful coaches. But a lot of people don't even think about this. They're just playing their sport, or they're just lifting. They're just eating this way because that's what they have in the house. And there's a lot of factors that go into it. But if you are a thoughtful person and you are saying, I'm just eating carbohydrates because it's what I need for fuel, and if you think otherwise, you're stupid, then I want you to comment below. So
Yeah, I think just to add on to that, I think another benefit of having an aerobic base, or not even an aerobic base, you can call it, because that's a little textbook too. It's just having mitochondrial efficiency, the ability for your mitochondria to use some of those byproducts of other energy systems and use them itself as fuel. I think that will actually improve your capacity of other energy systems itself.
that's true.
So just by having efficient mitochondria, you're helping yourself. It's pretty much just picking up all the mess that you're burning as you're going through. It's picking up all the mess and being able to recycle it rather than accumulating that mess and then feeling a burn because of some of those byproducts, such as hydrogen and increasing acidity in the cell.
I don't have any research to support what I'm about to say, but I would suspect that you probably not only have an improvement in your ability to repeat high intensity and maintain high intensity, but your capacity of that intensity will probably be way better if you have someone that doesn't train this way and someone that does slightly train this way. The capacity at which you can put that work through might be more efficient, depending. And if you look at ATP PCR, we didn't look at this, but just for example, how do you get that phosphocreatine back? So you have creatine and a phosphate. That phosphate just latches off to the creatine, and it's going to go and move your muscle. It's going to do it itself, right? It's high energy. So where does that phosphate come from? Where does that phosphate come from? It actually comes from oxidative phosphorylation, the aerobic pathway. So your repeatability for the highest intensity system that we have is actually relatable to your mitochondrial efficiency.
That's another good point. Yeah,
it goes back through. So what else? So that's our case on someone who's an athlete. What about our case for somebody who, going further though with the athlete part, I think putting this into practice, let's put it into practice real quick. So what do you do when you're in that off-season stage, earlier off-season? You do training where generally you don't go as hard, you don't feel the burn, you stay below your lactate or anaerobic threshold, and you train that way for a period of time. And you slowly increase the amount of intensity, but you have that endurance aspect. That's what we would do physically. Nutritionally, maybe we're not eating as many carbs. Cycle off carbs. Try and use more fat as fuel, maybe.
All right, because in the end, it's just all an adaptation. Like everything you do that to change, especially in the off season, especially if we're talking about the off season, you just want to make a whole bunch of adaptations in order to get you ready for the season. And if those adaptations are in line with your goal of being a better athlete and being able to perform better, then why not adapt to a more efficient or more flexible metabolism?
The more balanced you could stay metabolically, the better you'll be. And for some people, you're gonna want to be a little bit off balance to be a little bit specific to your sport, the energy system requirements of your sport. But the more balanced you stay metabolically, the better off you'll be as far as direct performance, longevity of performance day to day in practice, games, feeling better during the season, staying balanced metabolically, I think is key.
Health, injury, like all that, just being a generally healthy person.
Yeah. And look, I think do I think an off-season regimen or an off-season programming, I'm going to take an endurance runner that's running cross country. I'm going to train them very differently than a basketball player. They're going to be trained differently. They're going to be peaked differently. I'm going to gear a little bit more energy system allocation is going to be different. But I would say that it's not 90% this energy system, 10% this energy system. I would say it's probably going to be 70-30, 70-30, 60-40 range as far as prioritizing one energy system and not prioritizing another. It's not going to be this huge disparity. And that's where people get into trouble, is they just train this one energy system because it makes sense initially, but if you break down the physiology, it doesn't. And you break down metabolism, it doesn't really lie. And the science, the literature shows this too. You want to have this metabolic flexibility, and we know that.
Mm-hmm. So let's bring it full circle to someone who might have been told they have diabetes, or someone who has all those symptoms of metabolic syndrome. As long as you don't have anything else on the athletes.
No, go.
Good?
Yeah,
Right.
yeah. I think that's good.
So, for treatment for these patients, so diabetic patients and metabolic syndrome type patients, there is this new drug being used for them. It's relatively new. It's called SGLT2 inhibitors. It actually blocks the reabsorption of glucose in the kidney, and this causes you to piss out a bunch of glucose and ultimately lowers your total body glucose. So as we were saying, that's the issue, the total body glucose, not just the glucose that resides in your blood. So in contrast to the other diabetic medications that, the older medications and the insulin shots, this drug is actually on the right track, because rather than shoving more glucose into tissues and keeping your total body glucose the same just to mask the blood glucose levels, it actually gets rid of the glucose entirely by sending it out the body through the urine.
And I want to say something on that point. And I really like how you're bringing up a drug that I like how you're bringing up a drug and you're having a positive outlook on it, because it shows we're not purists, We're not like, oh, you have to just eat real food, you have to do this, you have to do that. No, we're not like that at all. We're
not monks.
We're not monks. We're about doing the right thing that the science proves, our intuition shows, and the literature approves, and our experience. We're talking about this drug, and it could work, and it could be beneficial. We're not purists, but the problem is a lot of drugs don't work. Why? Because there's no free passes in metabolism. There's no free passes in physiology.
There's no magic pill.
But I really like this, that you're bringing up a drug that works, because it shows we're not about our profession. We're not advocating for identifying with our profession. We're identifying with what is right for a human being,
Right, and as just like any other drug, it'll have side effects. So they include UTIs, infections, because you're peeing a lot and there's a lot of sugar in your pee, and kidney issues, frequent urination, and other complications. So again, just like any other drug, it does have its side effects, and it's out of our specific scope of practice. We are not allowed to prescribe drugs specifically. We are strength conditioning specialists, and we are doctors of but we're not allowed to prescribe medications like that. We can prescribe other things. We don't want to just be slaves to the healthcare system, though, and refer our patients to other doctors just so they can get prescribed medications that will lead to bad side effects and just further progress their diseases. So we tend to prescribe other things to them. So for a person with a diabetes or metabolic syndrome type, higher end on that spectrum, once you understand the concepts of what's going on physiologically, as we discussed in length throughout this podcast, you can begin to apply some treatments that'll help your patients. So,
and can I bring up one thing, bring it a little bit full circle to what you're saying, is that this is the problem. And we're bringing back this physiology. We're going through the physiology, and then we link it all the way up to the problem with the healthcare system and PT, is that we know the right thing to do. These doctors still think insulin resistance exists, for example. If you're a physical therapist that relies on a physician referral, what's going to happen? It's almost like a pay for performance. You need to listen to them, or else you don't get patient or clientele. You don't get money, you go out of business. So it's a big business scheme happening here. So if the doctor says, I want this patient to do this, we don't think otherwise. We are in a bad situation. And this is the situation we will not be dealing with. And that's why we're doing what we're doing. We're not labeling ourselves as this or that, being slaves to the healthcare system. I think what PT is going to help us with, however, is our scope of practice. Legally, what can we do for a person? And that's why it'd be really cool to have your doctorate in nurse practitioning so we could prescribe any medication we want. But we'll get somebody for that down the line. But I think that's a really good point that I just made, and I'm a genius, is that I really like the route we're taking, because we're not going to be slaves to this whole system, and we're not going to go through this vicious cycle of money being like, we want money. I'm not saying we don't like money, but not this way. Not at the expense of a patient, not at the expense of a client. We don't want money. But other people do, like this whole COVID thing. They'll put somebody on a ventilator to get triple the amount of money. So that's my spiel. Go ahead.
No, but yeah, once you understand these concepts physiologically, what we're talking about, then you can start to apply treatments to the patients. And rather than just robotically prescribing medications or interventions that you learned in a textbook, and neglecting the fact that you're actually harming the patient instead of helping, because you don't actually know the principles. You just memorized everything you learned in school, which is most people in our cohort. So based on the
delete it.
Shit, I shouldn't have said that. Whatever.
It's okay.
So I'm joking. Based on
stop being pussies now.
So based on what we talked about, for these patients, I think one of the most logical treatment approaches to not be to overthink it, and would be a low carb diet, or as some people would call a ketogenic diet, once you get higher into that spectrum of fats compared to carbohydrates. Another thing is fasting, and also exercise. Exercise, we were, that's our thing, is exercise. That's what got us into this field. But exercise in this context might just be definitely beneficial, and it's definitely something you can add to the
good for the sustainability of your practice, but short term, maybe not.
Right, so short term, it's going to take a little bit for the benefits to kick in, and that's
but if we're looking at short term for someone with diabetes, and the things we could do with what you're talking about nutritionally, I think it's pretty remarkable. And just to go back, they are prescribing, so being a robot and all, people are being prescribed insulin, even when we think that they're insulin resistant, they're still being prescribed insulin. So insulin's not the problem, but they're given more insulin. And what does insulin do, everybody? It causes hyperinsulinemia. This causes anabolic problems, and this anabolic problem that signals the two leading causes of death in America: CV disease and cancer. So in essence, these doctors are prescribing cardiovascular disease and cancer And guess what they're getting in return? They're getting them in the hospital in return. So this is a little bit far-fetched, but it's possible, but I wouldn't go that far, because I don't even think a lot of these doctors are even that smart to realize that. Not that I'm that smart, but I just don't think they're thoughtful at all. Like, I'm not that smart. Like, it's not, people that listen to this would get these concepts, but they're just not even thoughtful. They're not even conscious.
We're also not getting paid hundreds of thousands of dollars right now. So you would think someone who's getting paid hundreds of thousands of dollars and has many people's lives in their hands would actually know this stuff. But
they probably know it somewhere, but they turn their brain off. That's the thing. They have that off switch. And they don't got to do anything anymore. But it's crazy, because they probably do get a lot of money, whether they know it, whether they do it intentionally or not. And this is just off the dome. They probably get a lot of money from prescribing themselves certain things, like these medications, insulin, aka killer drug, and they get them back, and they make a lot of money. Same thing in physical therapy. And I know we want to be quick with this pod, but I'm in rant mode. I had a piece of chocolate after dinner. I do that once a week. So
yeah,
now my sugar's
we said we
really
wanted
high.
to be under an hour, and I think we're coming up on 2 hours. But hey,
We'll do a 2-part thing.
No, whatever. Yeah, we can do a 2-part thing.
We can. So it's the same thing in PT. PT, you come in for PT, whatever you want to call PT, biomechanical problem. You come in for your low back pain. What do? Nothing. We do these stretches, we do this massage, we do these low-level exercises in general that are going to take time, take weeks, and time heals all wounds, quote unquote, but it doesn't get to the root cause of the problem. It'll help the source. What happens in essence, they leave. They're like, oh, that physical therapist that I worked with my back helped. What about my shoulder? I'll go back to him because he got me better for this. Whether the physical therapist knows it or not, they created this cycle. So if they don't know it,
pain in their head means some sort of injury. So let's go to the PT to fix that injury.
And for us, what would we do? We would say, what is this? We would look at everything. We would look at, what are you eating? Because we know how interrelated this is. What are you eating? What's your autonomic nervous system like? Are you more in a parasympathetic state, sympathetic state? And we could get very objective about this.
How much are you pooping?
How much are you pooping? Pooping is important. Poop emoji, So, hey, I would advocate for us. So if you got problems, if I were you, I would comment below with problems, because this is a once in a lifetime opportunity. You got, all right. That's fan.
Let's get back to this diabetic patient or someone who's on that far end of the metabolic syndrome. We talked about exercise, but another thing, as he said, was low carb or a ketogenic diet. So if you're not consuming a bunch of carbs, you won't be accumulating that glucose in your liver, and you're forced to shift your metabolism to more efficiently utilize fat as a fuel. So in essence, you would be metabolically shifting and being more metabolically flexible. Another treatment approach could be fasting, and just there's a lot of research on this, and maybe not for this population because people are scared to do it. And just like low carb ketogenic diets, what was like 5 years ago or so, their low carb diets were, if you were a doctor and you prescribed a diet like this to a diabetic patient, you were probably
burned at the stake,
burned and stoned. And now it's in the hi Didi. Now it's in the guidelines of diabetic treatment and intervention. So I mean that's just how medicine comes full circle. But 5 years ago, human beings weren't that different. So I just think it's such a disservice to just look at evidence-based stuff. So, and this is kind of sending us down another little rant here, but a lot of times what happens is in medicine is that in the medical science field is that they need evidence right away. Like if you come to their to do a board of people who are funding research, for example, and you bring up this idea, then they're going to be like, okay, where's the evidence for it? Because we're not going to put it into clinical practice until we have evidence for it. When in reality, that it's just not there yet. It's just slower because of this. And I think something that Jason Fung even mentioned too in Peter Attia's podcast is that this is why the seemingly most advanced aspect of medicine is infectious disease, because it's so quick of a process for their experiments. It's okay, you're sick, let's try this drug, do you feel better? Okay, what's your blood markers? Boom, quick. Does it work? Does it not work? What we're talking about, dieting and exercising, it's not that quick. It takes a long time, and that's why it's a lot slower in advancing.
But it's more sustainable.
It is more sustainable, but the healthcare system right now is not a sustainable system.
Mm-mm.
I'm done.
Good. So what I would say, you talked about a little bit so you can fast. So we know, research knows, this is true as day, that in order to live longer, you need to eat less. Simple. Organisms that are in a caloric deficit, caloric restriction, that organisms, they did a study in, I think it was mice. One group of mice ate regularly, whatever they wanted all day. The other group of mice didn't eat every other day, or they didn't eat 3 days a week.
So they had some sort of fasting and they ate less, significant less.
That group of mice that didn't eat that lived 30 to 40% longer than the other mice. And these are mice. These aren't humans.
And yeah, they're mice, so that 30 to 40% is a much bigger relative time frame compared to humans whose lifespans are a lot longer. But still, that what he's saying is just
it's astronomical.
It's science.
Ridiculous.
Science, and it's pretty damn radical.
It goes back to the anabolic problem that you have, is that in pretty much all tissues besides muscle, when you're at a certain point in life, you don't want any more growth, or else that growth means cardiovascular disease or cancer. So you want to inhibit that mTOR signaling pathway that says we're going to grow more. But in muscle, you want that mTOR signaling. You want more muscle growth. Why? You want to be able to store more glucose. You want to be stronger when you're older. You want to preserve your muscle mass. You don't want to fall when you're older. As far as longevity goes, this is one of the most important things. One of the most important aspects is, one of the most important determinants of morbidity is leg muscle strength. So, which is true. This is not out of my ass. It's a top 3. So when we look at that, it's pretty remarkable. So fasting, not eating, will make you live longer because you're not going to be having these negative anabolic effects. But let's compare some things. So caloric restriction. This is what people do when they won't be under time restricted feeding. So they'll eat whenever they want, but they just won't eat as much. They'll restrict their calories. So when this is done in the absence of time restricted feeding, this is actually a good thing. So some of the things that it does is, it's shown to improve your risk factors for cardiovascular disease, as we would expect, improve your quote unquote insulin sensitivity, and improve your mitochondrial function. So these are all just general things that are going to happen, your mitochondrial efficiency. So part of the problem, though, in general with not eating is humans like to eat, correct? So
I like to eat. Apples and bananas.
So one of the solutions to the problem is, I think for me and for most people, it's easier to say, instead of not eating as much all of the time, just say you don't eat from here to here. And psychologically, there's so many other benefits to this. First step, psychologically, this is a little bit easier to do. I just don't have to eat. Like, there's no other option. It's not, what do I eat? It's, I just can't eat from this period to this period, then I could eat. There's a lot of things as far as your hunger hormone, ghrelin, it's going to respond differently. And if you really look at human history, if we have food, we hunt food, we go get food. There's no fridge. You get food, you eat food. There's no saving food. You eat food, you go through periods of feast, you go through periods of famine. That's how your bodies work. You're tricking your metabolism by saying caloric restriction, and this is shown. So caloric restriction is probably better than no restriction at all. It's not a sustainable practice, first of all.
And it's not that simple.
And it's not that simple. But they say it was.
Because not all calories are the same, and not all carbs are the same carbs, like you were saying earlier.
Yeah, there's so much to it, but say you knew. Say you knew what caloric restriction meant for you without time-restricted feeding. There's going to be, it's definitely better than not restricting, because we know restricting is going to improve all these factors. But if you compare it to something like intermittent fasting, so a type of time-restricted feeding, where you eat 8 hours out of the day and fast for 16, which is not that crazy. That means you eat from 12 to 8. You're already not eating a lot throughout the day, but you just eat from 12 to 8. If you're matching the calories, you're controlling for the amount of calories, but if you look at a group of people that does the intermittent fasting, so 12 to 8 every day, to the group that doesn't have time-restricted feeding but still eats the same amount of calories as that group, what happens? Well, what happens is the people that do caloric restriction alone lose a lot more muscle mass. Why? Your body's not designed for this. When you go through, because you're eating less calories, so you have to break stuff down. But when you do an intermittent fast, your body has different protective mechanisms that it activates, as it should, because it's prepared for that, because that's what it was built for. It's built for fast and famine, feast and famine. So what happens? Your GH goes up, so your growth hormone, the thing that baseball players take, whatever. But you have it endogenously inside you. So that growth hormone goes to your liver, gets processed as this thing called IGF-1. So it's almost like insulin, but it's a little different. It's going to help you bring up muscle and maintain muscle mass, maintain protein in your muscle. So you don't get that extra benefit when you just do caloric restriction. That's one thing that happens, right? This is just intermittent fasting. So this is that eat for 8 hours in a day, fast for the other 16. So another thing that's going to happen is, as Angelo was saying and I was saying, is you're going to flip that metabolic switch a little bit. Your glycogen is going to decrease total, and your glycogen is going to decrease, and you're going to start using more, just on the continuum, a little bit more fat as fuel than you normally would, because you don't have as much glycogen. So as your glycogens drop, your fats go up, but then you eat, and then you start using glycogen again. What happens if you don't eat for a longer period of time? Your glycogen keeps dropping. The amount of fat, beta oxidation, and ketone formation keeps going up, right? So this is the metabolic switch that we're talking about.
Right.
And it probably most efficiently occurs, as far as the research shows, anywhere from 30 to 40% of a caloric restriction. So if that's around like 3 to 4 days per week, probably, that you're fasting. So say you fast total of 3 days a week, like fully fast, don't eat, you're not consuming any calories. That's probably when you get the most efficient metabolic switch. A lot of people aren't getting that. And as you can see, a lot of people don't have the metabolic flexibility we're talking about, and we're including athletes into this conversation. But let's look at that a little bit. So if we look at, and there's studies done on, before I move on, there's studies done on proving that growth hormone is this factor. So they take a group of people that intermittently fast, two groups, they're both intermittently fasting. One group, though, in the pituitary has their, or hypothalamus, wherever it's produced, has their growth hormone stopped. They don't let them produce growth hormone. What happens? That group loses 50% more muscle mass. It's pretty cut and clear if we look at it. That's crazy. It's a crazy amount. So they lose 50% more muscle mass. So this probably is a huge factor in your ability to maintain muscle. Another thing. So when we compare the alternate day fasting with the intermittent fasting, so the intermittent fasting being the 16-8, 16 hours off, 8 hours eating, to eating every other day, even when we control for the amount of calories that are taken in per week, we find that the alternate day fasting is going to have an increase, so many more benefits. So you're going to have the increase in the amount of IGF-1, so that hormone we talked about, and this is associated with almost negligible muscle loss as compared to the IF, which still has less muscle loss than the caloric restriction, but not as much maintenance as the alternate day fasting. And this is because the alternate day fasting is going to have more of that IGF-1. It's going to have more epinephrine and cortisol that are going to help mobilize fat for fuel. On top of it, you're going to have this process that begins called autophagy, and it's on a spectrum. It's going to come more and more about as you fast for longer periods. So this is a double bonus that you get from alternate day fasting is autophagy. So autophagy, how I put it, is I have an apple tree at home. So what you have to do to make sure that you're getting your apples is you have to cut the branches that aren't giving you the proportional amount of return per energy that you're giving it. So if I have a branch that's not producing apples, just cut those. Now all the energy is going into the fruit-bearing branches. So you're becoming more efficient. So this happens in a bunch of different tissues. This
And
happens.
it's not far off. Sorry to cut you off. It's not far off. It's not far off from. It seems like a far out analogy, but in reality, biology is biology, and a plant is a living thing, and so are we. And like, we're not plants, like we're not trees. We're one of the most sophisticated organisms on the planet, but still, biology in its most simplest state is biology. And so that I just want to put that out there.
Yeah, no, that's a good point. I didn't even think about that. So yeah, this autophagy, though we don't have branches, where does this happen? This happens in our skin cells when we have inefficient cells. Autophagy means to eat yourself. So you're eating all the inefficiencies. So all the things that aren't giving you proportional returns. So we're eating all the inefficiencies. What are we doing with it? We're not just throwing them away and discarding them and excreting them. We're recycling all the good stuff. So say this is a bad cell, but the mitochondria is good. Mitophagy. Say we really like this ER, this endoplasmic reticulum. We take that, we take this, we take that, but we get rid of the cell.
You're like junking cars.
Yeah, exactly. But we're taking things that we like.
Right.
So, and now we can use some of those products for, guess what? Muscle protein synthesis. So instead of getting your thought might be, oh, if you're not having this amount of protein, you're going to lose mass because it's all about calories in, calories out. No, you dingus. You're going to have autophagy, and you're even going to get a really valuable amino acid, leucine, that everyone loves to talk about. That's even going to come from other cells, right? So like your skin cells, your liver goes through autophagy, your pancreas, your nervous system goes through autophagy. And this is a cleansing process, and this is a process that I think all humans should go through at some point on some level. And I know that this is part of the mechanism that supports the research why alternate day fasting is going to help you preserve more muscle mass than 16-8. Intermittent fasting, really interesting, just on mice, a study. And if you want any of these studies, just let me know. Comment below. A study on mice. It's not humans, it's mice, but it's pretty crazy still. Two groups of mice. One ate as much as they wanted. Well, they both ate. No, back up. 2 groups of mice. Both groups, when they ate the same amount per day. So say they ate 100 calories per day. They both ate the same things in the same amount per day. One group ate 7 days a week, so 700 calories. One group ate every other day, so 350 calories on average, if we're doing this for weeks on end. The group that ate 350 calories per day on average, so the alternate day fasting group,
per week.
gained more muscle mass than the other group. This is in mice, but they gain more. I don't know if it may have reached statistical significance. I'm not sure, but they gain more muscle mass. That's pretty insane.
Even
So,
then, like just in terms of maintenance, that's people say like, oh, like you're gonna lose muscle mass because of nutrients and you're not gonna have protein. Like there's studies that show
is
it's not
fat.
true.
That is fat. Your fat is literally the thing that gives you energy. Why would your body use protein? It's going to use protein if you fool it and you do all this dumb shit like caloric restriction, because people do that and people say it's good. Oh, we have food, so we'll just eat it. No, you go through periods where you don't eat. It's a process. It's a different process. You flip your metabolism. All these things that we're talking about. I personally think based on the science, that whether you're an athlete, whether you're someone with metabolic syndrome, whether you're someone that wants to live to their 100, whether you're somebody that wants to improve their health, anybody, I think everybody on some level should be doing some sort of time restricted feeding regimen for so many different reasons. I don't think it's almost unquestionable in my eyes that everyone should be doing this, and people should start straying, and context is key, but everyone should start straying a little bit more away from caloric restriction. And this fasting, it's not a fad, it's science, and it's not a diet, it's literally not eating. That's what it is.
And a lot of it has to do, just to wrap up with like implementing it and stuff. A lot of it, you tell someone to fast, I think you said this, like you told your parents you were fasting and they thought you were crazy and like you're stupid, this and that. But why did they say that? Because society makes you think that if you miss a meal, you're so unhealthy. Like all of a sudden, breakfast is the most important meal of the day, right? Where did that come from? Like what? That there's no science to back that up, or if there is, it's very misconstrued science, and it's probably unhealthy people in the first place that they studied. But that's a whole other rant. But it's just, take it the opposite end of the spectrum. People who fast for religious reasons might be a little more, willing to partake in an intervention like this for their health, because society, like in their social groups, there's people who also do it and they are willing to do it for that reason. So if you live with people who fast certain weeks of the year, then they'll probably be more inclined to do it. So I think there's a lot of approaches to fasting, and as he was saying, there's intermittent fasting on one end of the scale, and then there's also alternate day fasting and several days of fasting on the higher end of the scale, and it even goes further than that. There's crazy people who didn't eat for days on it, months on that, and it's insane. But I think there's a lot of different approaches for your patients and how to implement these interventions and treatment approaches for, as you said, a lot of different reasons, and it just depends on where they are on the spectrum.
Yeah, and to go back to what you said earlier about how slow science is, and you're talking about religion, so a benefit of not slow science, how slow literature to come out is in research, and people are slaves to the research, but it's so slow. But the benefit is it's usually pretty good as far as the information. It's easy to depict information from it, but it's so slow. On the other end, you have gurus, religion, other aspects like that, which are really fast at,
because it works, but they don't know why. Perhaps
it worked for them, their experience, or what have you, or religion. These are things that you get information really fast, but it may not be as accurate. The accuracy
It's not
drops.
supported via objective measurements in a lab.
Yes, exactly, because for multiple reasons. So I think that, yeah, just you can't be a slave to the research.
But when
you
you,
have to.
yeah, I think what you're saying is when you combine those two things and think for yourself and take the best of both of them and the worst of both of them, you can implement your own techniques and your own approach to things.
Yeah, and you'll see what works. And every there's no, it's not always cut and dry. We're always learning new things. Everyone's always learning, or unless you think you know it all, because then you stop learning. But everyone's always learning, and you're going to have a patient or client one day that you don't know what the hell is going on, and you don't, and that's okay, because you're not going to know everything. But everything is science. Every patient is an experiment to some extent, because you're trying something.
Everyone's different.
It's the scientific method. You have a hypothesis, and you have a method, and you have results, you have outcomes, you have conclusion, and you have discussion. And that's science. That's how you approach things in a logical manner. And if it's not the scientific method, it's not science. I don't think it has to be research to be science. You have to go through the scientific method in some way for it to be considered science. So every patient that you deal with, every situation that you deal with, should be approached scientifically and thoughtfully and logically. And in that way you'll constantly learn. So you're constantly monitoring, you're constantly measuring outcomes, going back to their baseline and seeing what's working and applying it back to the science, your experience, and partly informed on the evidence, but definitely not a slave to the evidence. And if you're a slave to the evidence, I honestly feel bad, because you're not going to grow. You're not going to grow that way.
If you take all that information that you're continuing to monitor from your patients and continuing to get from each patient, and you approach it in a more holistic way, which is our approach, rather than thinking of it in such a specific lens, such as just as a PT, I think you will benefit from not limiting yourself in that lens.
Yep.
And
Wait.
I think that's
you done?
Yeah, I think that's a good
All right. Yeah. So just
wrap.
thank you for sticking along. But yeah, there's definitely so much more about this topic, like metabolism in general, that we didn't touch on today, but we will touch on. If, like I always mention throughout the podcast, if you want any of our literature that we have or more explanation of the science, we'll definitely be happy to help. Just comment below. And just don't take, obviously, we're not offering any medical advice. This is not to be taken as medical information, just to cover ourselves.
Mm-hmm.
And
in other words, don't listen to anything we say.
Yeah, in other words, don't listen to us. No.
The end. Goodbye. We love you
but
all. Peace, love, tranquility.
But honestly, if you guys enjoy this, just leave a like and a follow, and leave a comment. Interact with us a little bit. Check out our Instagram, AR Human Performance Doctors.
AR Doctors.
Oh, it's AR Doctors, our username. But okay, that's what matters. All right, till next time.
Adios, muchachos.